The topic that I'm going to be speaking on is scientific software design. This is similar to the slide you saw in David's introduction. So here, again, the left side of this figure should seem familiar to you because this was also mentioned in David's presentation. I want to use this to highlight that for the last, I would say, 20 years or so, there has been high performance computing somewhere in the beginning of 2000 started to use the distributed memory model with clusters. And so in the distributed memory model, what was happening was that this part of the slide where there's a positive feedback loop cycle between the growing understanding and growing complexity of the software was true. And so you see this red line, and this was roughly how the software complexity was increasing, but the platform complexity was not increasing proportionately. And then as the Dennard scaling stopped and we couldn't just keep getting more performance out of increasing the clock rate or by the heterogeneous models of computing got introduced, the platforms became more and more heterogeneous to the extent that almost all machines these days have some form of a special purpose device like accelerators. Now what has happened is our complexity, the software complexity has continued to increase because of better scientific understanding and higher fidelity models, but at the same time, platform complexity has been increasing tremendously, and so this is the line along which our overall complexity is growing, and therefore, what used to be not paid attention to very much by people, that is the software design, has all of a sudden become a critical issue. So some of these general principles for HPC scientific software have always been valid. What has always been true is that we work in multidisciplinary teams because there are many facets of knowledge. And it's not possible for anyone to know everything that is involved in writing software because it involves expertise coming in from the domain scientists, the applied mathematicians, the software developers, and the people who do performance engineering. And so what that implies is that in the design, there should always be separation of concerns, which means that the software ought to be designed in such a way that developers should be shielded from the complexity that they should really not need to know anything about it. As an example, in the era of distributed memory parallel computing, a good separation of concerns was to keep the parallel aspects of the code separate from the numerical aspects of the code. And that would usually suffice for there to be enough separation of concerns for people to be able to do their work so that the numerical code parts of the code looked almost sequential, whereas the parallel parts were encompassed in these few primitives that took care of most of the internode communication that needed to happen. Then there's two types of code components. The one type of code component is what handles the bookkeeping, the infrastructure, such as the discretization, which includes things like the mesh, the particles, the I/O, the runtime, etc. The implication of these are that these should be longer lasting. They don't change very often. And then there is the science model. Science models are the parts of scientific software that are subject to most rapid changes because they incorporate research that is coming in from the science domain as well as from the applied math. And so these two components ought really to be working with different life cycles. One should be a long-lasting life cycle versus a quick-changing life cycle, because what is also true about these two different types of components is that the infrastructure is logically complex but mathematically simple, whereas science models tend to be logically relatively less complex but mathematically very complex. The other consideration that goes into designing of HPC scientific software is that codes grow. That is, every time a code is exploited in a scientific campaign, there are always new ideas, and therefore always new features are added, and codes tend to be reused by others. So they're almost always used for purposes other than what the original designers of the code intended it to be. And therefore, it is important to build extensibility in order to add the new capability. It should be possible to have that kind of extensibility and also the ability to customize existing capabilities. So the appropriate way to look at design of the codes is through the schematic. What the schematic is that the purple parts of the code are the more standard, more stable parts of the code, mesh, discretization, etc. And the infrastructure that handles the data structure, the data layout, and movement. And then there are the client code, which is mathematically complex and is the research subject. So what you do is you treat them differently and encapsulate them in ways that that plug and play is enabled, so that you can plug in the scientific parts of the code into the infrastructure as you need, and the capabilities are provided by the infrastructure to these client codes as they need. Certain things apply to both kinds of codes, and that is that as far as possible, they should be enclosed in logically separable functional units of computation or modules. That logically separable functional units should be encoded into a framework that then define interfaces through which these various types of codes interact with one another. And within each of these modules, there should be a differentiation between protected and public interfaces. And this is basically to hide the complexity of one type of code from the other. The other important principle to remember is that the design should happen before a programming model is applied to it. Because what you really want to do is understand the structure of your code before you wed it to a specific programming model. Because if you started to do the design based upon a programming model in mind, it is quite likely that you will not explore the entire design space and you will end up with a suboptimal design. So a model for achieving separation of concerns is sort of captured by this schematic. Here we have two different flow graphs that interact with one another for in a few defined spaces. So for the infrastructure, the life cycle or the flow graph is that you collect requirements. This is important because this is the part that is the server and is the slow changing and therefore needs to be robust and extensible. And so you do requirements gathering for it. You device, encode that in our software architecture, and design APIs so that the services are offered by this infrastructure to what I call the physics capabilities. They have to be implemented, tested, maintained, augmented, etc., as the code grows. The second part of it is what I have been calling the client code. And for them, there is this cycle: design, develop, and validate. This can happen completely outside of the framework. This people can even do in Python or MATLAB, basically build their prototypes, implement their algorithms, convince themselves that they have all the characteristics of stability and convergence they need. And then they can translate them into an appropriate other language such as C, C++, or have a code translator do this for them. And I don't know why this is advancing. Encapsulate that into an API and then integrate that with the infrastructure. And so the infrastructure here is informing the model as to what are the requirements of the API, and the API is designed appropriately. When it needs to be integrated, often this augmentation should be actually a null set, but sometimes it may be necessary to augment the infrastructure. But these really should be the only points of interaction between the infrastructure and the capabilities. If you've achieved this, if you've largely achieved this, you will have had a good separation of concerns built into your software design. So I want to give an example of how to do software design with a running example. The website that David pointed to in the introduction is about this heat equation where it is a solution for this problem where you say you're in a house with the exterior walls that are made of a single material. Inside of it, there are some water pipes, and then there is the outside temperature and the inside temperature. And you want to be able to determine what should be the whether if you maintain this kind of temperature, will your pipes freeze over before the storm is over? And these are modeled with heat equation for which a solution exists in the repository that you can see. But I want to walk you through the steps of how that solution would have been obtained. So the problem specification and the design considerations that go into designing that software. The specification is that we have to solve heat equation with some initial and boundary conditions. We want to have ability to implement different integration methods. And so we want to be able to say, use different kinds of numerics depending upon what is the fidelity of answer we want. So the consideration is, what is our infrastructure here? Our infrastructure is whatever is the discretization, which means the state, which would include things like the temperature, primarily the temperature in this instance. Verification, the IO, using which we are putting out the calculated values, application of initial conditions, runtime parameters, and comparison utility. Our model here is the initial conditions that we are applying, the boundary conditions, and the integration method. So if you look at the repository, what you will find is that there are these functions available, which is the processing of the arguments, the copy, this is the output. So here is the input happening, here is the output happening, and the initial conditions are set in this particular function. So this is our infrastructure API. The Numerics API is for calculation of norm, the actual calculation of the capabilities, update solution using various methods, which is here, there is Crank-Nichols upwind, exact solution, etc., etc. So all of this is the numerical API in that particular design space. So that was just an example of what a toy problem would do. Now, what if you were looking at a real life example? And so here I'm taking an example of multiphysics partial differential equation based a code that I'm most familiar with. So in doing the design here, what we do is we take a real view and a virtual view. The real view is that we have a whole domain with many physics operators. By operators here, I basically mean physics solvers. So what we want to do is spatial decomposition, because we are operating in HPC zone, which means that we will be using distributing work among different processes. And then there is the functional decomposition in order to allow for some sort of encapsulation and modularity. And so our virtual view from spatial decomposition is basically that we have these domain sections, which are standalone computation unit. And this I'm explaining in the context of explicit methods where this kind of an abstraction where you have cells, the black cells here are the ones where you're updating the values, surrounded by halo of ghost cells, which come from the neighboring areas, basically present a standalone computation domain to the operator. So the operator can't tell the difference between the whole domain and this subsection of the domain. And then each operator is basically a collection of components. And so now we have separated the concerns here where parallelization, and in the distributed memory parallel view, if we were implementing this, then the separation of concerns would be that parallelization and scaling optimization would be happening in this virtual view, whereas the memory access and compute optimization will be happening in this virtual view of collection of components. So here, this is implemented by domain experts and applied mathematicians, and these parts are then implemented by software and performance engineers. But now what is happening is we are in this mode where the heterogeneous models have happened, so we need to reconsider how we are doing the design. So the question is, does the whole design process change fundamentally? And the answer is no. If we have taken care to do this separation of concerns, then what really needs to happen is that the portions in this figure that are surrounded by the purple ellipses is where the actual changes happening can be limited. And what happens is that in these just the principles remain the same, in that you are looking at slow changing code and fast changing code, and that you are making sure that the interfaces are happening at relatively limited places. But these processes become more detailed, and they become somewhat more complex. So from the previous situation, if we were to be looking at the if we were to be looking at partial differential equation based solutions, now in the virtual view with domain sections as standalone computation unit, now we have two different aspects of optimization that are happening here. There is the load distribution, and there is the runtime management. The load distribution is still making sure that the work is distributed roughly along the coarser unit of computation in the parallel environment. And the runtime management then is making sure that that the specialized devices like accelerators are effectively used within the node. And so that kind of offloading and scaling optimization is now managed by these two different components, though they are still, if you're looking at the previous figure, they're still encompassed within this part of the feature. It's just that the API will be more fine-grained and richer. Similarly, the virtual components of the view remain still the same. This is still implementing the numerical methods and the model, but now what we may have to do is have abstraction at the solver level, which may then encounter a need to do code transformation so that you don't have to have combinatorial explosion of maintaining a different version of the code for each different device that you may be supporting. And that will still be doing the memory access and compute optimization. So with that, the takeaways from the design that we have from what I've outlined so far is that it is important to differentiate between slow changing and fast changing components of your code. For the slow changing component of your code, you should take your time to understand the requirements and design the infrastructure. You should implement separation of concerns. And from the beginning, you should design with portability, extensibility, reproducibility, and maintainability in mind. You should leverage existing capabilities where possible. And with that, I come to the end of this section of the presentation.